Welcome to another tutorial in ME Review. Today, I will be discussing engineering calculus. In the previous lesson, we discussed algebra, trigonometry, solid mensuration, and analytic geometry. At the end of this lesson, you should be able to recall the fundamental concepts and principles in engineering calculus, list important formula and equation in engineering calculus, and apply these concepts, principles, and formula or equations in solving worded problems in engineering calculus. This will be the outline of my presentation. It is divided into differential calculus and integral calculus. Let's start first with differential calculus. Beginning with derivative. The function f prime x, defined by the formula that you can see here, the limit of the function x plus h minus f of x over h as h approaches 0, is called the derivative of f with respect to x. The domain of f prime x consists of all x in the domain of f of x, for which the limit exists. The notation for the derivative can be as shown here. It could be in a form of f prime x, a y prime, or a dy dx. All of these are equivalent to our previous limit. Differentiation formula. Some of the formula that will be used in differentiation are, first we have the basic formula that you can show here, that you can see here. We have the product rule, the quotient rule, the power rule, the chain rule. We also have the formula for the exponential functions, logarithmic functions, trigonometric functions, inverse trigonometric functions, hyperbolic functions, parametric equations, and the higher derivatives. Sample problem number 1. Derive the function square root of x to the power of 5 plus 1. In this problem, we are going to apply the chain rule. The chain rule is defined as the derivative of the function of u with respect to u is equals to df du multiplied to du dx. So in order for us to obtain this formula here, we'll first examine our given equation. So in the given equation, our function is equals to the square root of u because it is in the form of a radical. So we can equate u as the value inside the square root, which is x to the power of 5 plus 1. So if we're going to put this in our equation in the chain rule, then we will have d over du multiplied by f, which is the square root of u, multiplied by the value inside the radicand, which is our u, which is x to the power of 5 plus 1. So we can then differentiate each of these quantities separately and multiply them. So for d over du of the square root of u, in our equation in the formula, it is equals to 1 over 2 square root of u. So therefore, we can already have the first part here of our chain rule. Then, the derivative of x to the power of 5 plus 1 is simply 5x to the power of 4. So we will substitute this value in our equation. So we multiply the two results that we have, this one and this one. So that's why we have this product here. Then we are going to express our equation back in terms of x because it is really in terms of x and not in terms of u. But we know that u is equals to x to the power of 5. So we are going to substitute back x to the power of 5 plus 1 to our u. and then we're going to simplify it. So by simplifying it, we will obtain 5x to the power of 4 over 2 multiplied by x to the power of 5 plus 1. So that is how you can solve this particular problem. You can actually use the simple formula du dx over 2 square root of u, or the derivative of what is inside this radical, which is 5x to the power of 4, so that is our du dx over 2 square root of u, which is x to the power of 5 plus 1. So it will become easier if you are familiar how to get the shortcut derivative of a square root. Then we have y is equals to x plus 1 over x plus 2 squared. So this is a quotient of two polynomial, x plus 1 and x plus 2 squared. So we are going to apply the quotient rule since this is a quotient. So in the quotient rule, our f over g prime, which is represented by our given, is f prime g minus g prime f over g squared. So in our given, our f prime is the value x plus 1. So this is our f rather. And our g is the value in the denominator, which is the x plus 2 squared. So if we apply the chain rule, we first get the f prime. So our f prime is the first derivative of x plus 1, which is this one. So we have d over dx of x plus 1. Then we have this one. This is the f prime multiplied by g. So the g here is the denominator. So we put that back here. So that's why we have x plus 2 squared. Then minus g prime, or the first derivative of the denominator, or the d over dx of x plus 2 squared, multiplied by f, which is the x plus 1. So we simply follow this quotient rule here over g, which is x plus 2 squared, to the power of 2, because it is squared here in the formula. Then we are going to calculate each of these d over dx here. So the derivative of x plus 1 is simply 1. So that's why we have 1 here, because the derivative of 1 here will become equal to 0. The derivative of x plus 2 squared is simply, you put down 2 and then apply the power rule, x plus 2, 2 minus 1. That's why we have power of 1 here lang. And then we're going to put these values here in the formula back. So we have the d over dx of x plus 1 is 1. And the d over dx of x plus 2 squared is 2x plus 1. So substituting the value and then simplifying, we can get the derivative as negative x over x plus 2 cubed. Sample problem number 3. We have y is equals to 2 to the power of tan 4x. So this is actually an exponential equation. So we can apply the exponent rule. So the exponent rules, this is not yet the we are not yet differentiating, but we can use this exponent rule in order to simplify the given problem. That a to the power of b is equals to e to the power of b ln a. So from the given, we can take a as the value 2 and b as the tan 4x. So that our a to the power of b, which is 2 to the power of tan 4x, is equals to e to the power of b, which is tan 4x, ln a, which is ln 2. So we simply substitute an exponent form of this equation here. And then we are going to apply we are going to derive it by applying the chain rule. So we have the d over dx of e to the power of tan 4x ln x. So the chain rule is defined as follows, which is the same as what we obtained from the previous example, of course. So applying the chain rule, so our f is equals to the e to the power of u. So because this is representing our whole equation, so that's e to the power of u. And our u is the value tan 4x ln 2. So our f here represents an exponential equation e to the power of u, where the value of u is the one that is being the power of e, which is tan for x ln 2. So we substitute this value in the chain rule. That's why we have d over du of eu multiplied by d over dx of our u, which is tan for x ln 2. Then we know that the derivative of eu is also eu. On the other hand, the derivative of tan for x ln 2 is, first we can separate this constant ln 2 because it's a constant. No need to differentiate that part. So we will just put that here separately and multiply it with the derivative of tan 4x. So for tan, the derivative of tan x is secant squared x. So that's why we have here secant squared 4x, because the value of the angle is 4x. And since it still has 4x here, we need to differentiate it also. That's why we have here 4. So that's why we obtain by substituting the value of EU. So we have here EU and then the value ln 2 secant squared 4x multiplied by 4. Then we substitute back the value of u here, which is tan for x ln 2, so that we obtain this value here. And then we just simplify so that we'll obtain the final result ln 2 multiplied by 2 to the power of tan 4x plus 2 multiplied by secant squared of 4x. Derive e to the power of x plus y is equals to x plus y. If you're going to look at the problem, y appears in both sides of the equation. That's why we can apply here implicit differentiation. So in the implicit differentiation, we're going to differentiate each of the term. So we are going to differentiate the left side, which is e to the power of x plus y, and the right side, which is the x plus y. So d over dx of bx plus y is equals to, because we know that it's just eu du dx, that's why we have here our eu is the e to the power of x plus y, and the du over dx is the power, which is the u, which is the x plus y over dx. And that is equals to the d over dx of x plus y, and we know that that is equals to x plus y, xy prime multiplies y x prime. So x prime is equals to 1. That's why we have no value of x prime here. Then we're going to differentiate the value of x plus y. So that by differentiating it, so the x is just equals to 1 and y will be equal to y prime. Then we're going to solve for the value y prime. So putting y prime terms together, so we obtain this equation, and then we're going to extract y prime, and then finally we divide both equations by e to the power of x plus y minus x, so that we can obtain the value of y prime. So and that represents now the first derivative of the given function. Sample problem number 5. Derive y is equals to log 6x minus 7 to the base of 4. So we can use the formula for differentiation for logarithmic equation. So applying log rule, so we have here the log rule. The log of b to the base a is simply ln b over ln a. So it's a general formula. So that's why our given equation can be written as ln b, which is our 6x minus 7, and the a here is the base, which is ln 4. And we differentiate it because that's what we are looking for, the derivative of this equivalent equation. So if you can look at the given equation, we have here a constant ln 4. So it doesn't carry a variable, so it's a constant. So by applying the constant rule, we can take out the constant so that we will have 1 over ln 4. And then the derivative of the remaining equation, ln 6x minus 7. And then since we have here a function then we will apply the chain rule in order to obtain the derivative of ln 6x minus 7. So by observing the given equation, we can find that our function is equals to the ln of u, or that is the u, which is equals to 6x minus 7. So putting this value in the chain rule formula, we will obtain this 1. And then we also included the constant 1 over ln plus 4. Then we are going to differentiate ln u and also the 6x minus 7 separately. So d over du of ln u is simply 1 over u. For 6x minus 7, that is equals to 6. And then we have our, by substituting all of these values to our working formula, then we will obtain this 1. And then substituting back 6x minus 7, then we will have this 1. Then simplifying that equation, we will obtain 3 over ln2 6x minus 7. Okay, we have sample problem number 6. Derive y is equals to 2x to the power of 5 hyperbolic cosine of x. So if you're going to look at it, we have two function rather, that is being multiplied. So we can apply the product rule because it's a product of two functions. So the product rule is f prime g plus f g prime. So where our f is our x to the power of 5 and our g is the hyperbolic cosine of x. So that's why by putting this in the formula for product rule, we will have the constant because no need to differentiate that. The d over dx of x plus 5, which is the f prime, multiplied by g, which is hyperbolic cosine of x, plus the first derivative of g, which is the hyperbolic cosine of x, multiplied by our f, which is x to the power of 5. So based on this equation, we will have to differentiate x to the power of 5, and that is 5x to the power of 4 by applying the power formula. Then for the hyperbolic cosine of x, that is simply equals to the hyperbolic sine of x. So putting back these two results in our working formula and simplifying it, then we will obtain the value 10x to the power of 4 hyperbolic cosine of x plus 2x to the power of 5 hyperbolic cosine of x. Then we have hyperbolic cosecant of pi x. So we still apply the chain rule because we have here a value pi x in the angle of the hyperbolic cosine. So the chain rule is given this way. So our primary function is hyperbolic cosine of u, where u is the angle pi x. So by applying the chain rule, we will put all of this in the formula. So our f is the hyperbolic cosine cosecant of u multiplied by the du dx, which is the d of pi x over dx. Then solving for the derivative of hyperbolic cosecant of u, that is simply equals to hyperbolic cotangent of u multiplied by hyperbolic cosecant u. And then for pi x, that is simply equals to pi because pi is a constant. The derivative of x is 1. So that's why we have pi. So putting this result in the working equation, then we will obtain this. Then we will have to put back the value pi x. And then simplify, then we can obtain the result negative pi hyperbolic cotangent of pi x multiplied by hyperbolic cosecant of pi x. Then we have the tangent of xy is equals to x plus y. So looking at it, we have an implicit function, and then we have to differentiate it implicitly. So we will differentiate the left side and the right side. So for tan xy, that is equals to secant squared xy. Then the d over dx of the function inside the secant. So that's why we have here xy is equals to d over dx of x plus y, which is simply 1 plus y prime. And then for x plus y, that is xy prime plus y. Then we are going to put the y prime terms together. Then extract y prime so that we can get the value of the first derivative. Derive y is equals to arc sine of x squared. So we are going to apply the chain rule for this given equation, where our f is the arc sine u and our u is equals to x squared. So applying the chain rule, we will put the value of f first multiplied by the derivative of the u, which is x squared. So the derivative of arc sine of u is 1 over 1 square root of 1 minus u squared. For the derivative of x squared, that is equals to 2x. So putting this value in the working equation, then we will obtain this 1. And putting back the value of x squared, simplifying it, then we will obtain 2x over square root of 1 minus x to the power of 4. Then finally, we have y is equals to the arcot of 5 over x. So we'll still apply the chain rule, where our f is arcot of u and our u is equals to 5 over x. So putting the value of f and u in the chain rule formula, and differentiating first the arcot, that is just negative 1 over u squared plus 1 in our formula. And the derivative of 5 over x is simply negative 5 over x squared. So putting back this in the working formula and substituting the result by putting back 5 over x again, then we will have 5 over 25 plus x squared. So as you can see, majority of the problem deals with the chain rule and also the basic properties, the product rule, quotient rule, the power formula, and all of those techniques that we can first simplify the given equation and then differentiate it. So let's proceed to the L'Hospital's rule. So the L'Hospital's rule states that the limits remain the same even if the numerator and the denominator are independently differentiated. So if you're going to differentiate the numerator and denominator, the value of the limit would still remain the same. And we can use that rule in order to determine the limit of given functions by differentiating both the numerator and the denominator. So this rule applies to indeterminate forms. The indeterminate forms are those values that will give us an infinite or a value that is not defined, like 0 over 0 and infinity over infinity. So let us apply the chain rule in this given problem. Evaluate the limit of x cubed minus 14x plus 15 over x cubed minus 13x plus 12 as x approaches the value of 3. So according to the chain rule, even if we're going to differentiate the numerator and denominator separately, the limit would still remain the same. So we can equate the given limit to the limit of the quotient, wherein the numerator and the denominator are already differentiated. So for x cubed minus 14x plus 15, it is differentiated as 3x squared minus 14. And for the denominator, that is equals to 3x squared minus 13. So we will try to plug in the value of x, which is equals to 3, and see if we can obtain a value that is defined. So substituting the value of the limit, which is x equals to 3, and then solving for that value, then we will see that it's equals to 13 over 14. Since the value is already a value that is defined, meaning it exists, it's 13 over 14, then it's the limit of this given equation here. So an alternative to this is to first factor the given function, and then you can cancel out common factor and apply the value x equals to 3. But that would take that's a longer solution as compared to applying the L'Hospital's rule. Then we have the limit of 1 minus cosine x over x squared. So we are going to apply the L'Hospital's rule by differentiating the numerator and denominator separately. So that's why we obtain for 1 minus cosine x, that is equals to sine x. And for 2, for x squared, that is equals to 2x. So if we're going to substitute the value of x, which is equals to 0, then what we will obtain is our uh, cosine of 0, which is if we're going to obtain the value already by substituting the value of 0 from this first equation, we'll actually obtain a value that is not defined, which is equals to 0, because the sign 0 there would be equals to 0. Then divided by 2, which is 0, would also become 0. So that means that we'll obtain a value that is indeterminate. So that's why we can still differentiate this until we will obtain a value that is already defined. So for sine x, the derivative is cosine. And for 2x, the derivative of 2 is 2. And then by this, we can already substitute the value of 0 to x to obtain a value that is already determinate. So that is equals to 1/2. So that's one advantage also of the L'Hospital's rule, because you can uh, differentiate as many as you can, as long as you are confident that you will obtain a value that is determinate. Then the slope of a curve. So this is one of the application of differential calculus. So wherein we can get the slope of a curve by differentiation. So a line is a curve with a constant slope. For curves other than line, the slope of the curve is equal to the slope of the tangent to the curve at the point. So the slope of a point xy on the curve can be obtained by deriving the curve and then substituting the value x plus y. Say for example, we have here this given curve, and we are concerned with getting the slope at this point here. So unlike a straight line, we cannot get that readily because the equation is the equation of a curve. Unlike a straight line, we can get the equation directly. But for this, we can use the rule that we will first get the first derivative, or the y prime, and then substitute the value of x and y of that point to the y prime in order to get the slope of this tangent line at that particular point in the curve. So you can do that in any place here in the curve. So let us have an example. So find the slope of the circle x squared plus y squared is equals to 25 at the point negative 3, 4. So this is the circle. So it has a center at 0, 0 because they don't have a value of hk. The radius is equals to 5 because that's just a square root of 25. And then the negative 3, 4 is located here, and we are concerned with the slope of the circle at this point, negative 3, 4. So it refers to the slope of the line that is tangent to the curve at that point. So in order to get the slope, we're going to differentiate the given function of the curve, which is the curve, which is a circle. And you can notice that we will have to apply implicit differentiation in order to get the y prime. So derive x squared plus y squared is equals to 25. So that would be equal to 2x plus 2y y prime is equals to 0. Then we solve for y prime, so that is equals to negative x over y. And then we're going to substitute the point wherein we are going to get the slope, and that is negative 3, 4. So we have x is negative 3, y is equals to 4. So substituting and then simplifying, we can get the slope, or the y prime, which is equals to 3, 4. So from this example, we can understand that the slope of the curve is equals to the first derivative, or the value of the first derivative. Then we have the tangent, a normal to a curve. So for the equation of the tangent line, it is defined as y minus y sub 0 is equals to y prime o multiplied by x minus x sub o. For the normal line, or the line that is normal to the curve at that point, that is simply 1 minus y prime y sub 0 minus 1 negative 1 over y prime sub o multiplied by x minus x sub o. So you can see the only difference is that the slope here will become the negative reciprocal, because if we are going to recall, the relationship between the slope of parallel and perpendicular lines. So if they are perpendicular, then the slope would be the negative reciprocal. So that's why we have here negative 1 over y prime o for the normal line, because that's a perpendicular line. So to illustrate how to use those equation, let us have an example. So find the equation of the tangent and normal to the curve xy is equals to 4 at the point 1, 4. So if we're going to trace the curve, this is actually a hyperbola. So this is the hyperbola, and then we are concerned at 1, 4. And then we are to locate the equation of the line that is tangent. So the tangent is the blue line, and then the normal or the perpendicular to that point is the green line here. So we are going to solve what is the equation of those lines. So by performing implicit differentiation of the given curve to obtain the y prime, so that our xy will be equals to xy prime plus y, and 4 is equals to 0. So that's why our y prime is just equals to negative y over x. So from this, we can get the value of y prime. So substituting the value of x sub o, which is equals to 1, and y sub o is equals to 4, because that is the value of the coordinate of this point. So our y prime is negative 4. Now that we have the y prime, we can get already the equation for the tangent line, because it's defined as y minus y sub o is equals to y sub o prime multiplied by x minus x sub o. So substituting the value of x sub o and y sub o, and also the value of y prime, then simplifying and rearranging, we can get the equation as 4x plus y minus 8. So this is the equation of the blue line, which is the line tangent to the curve at 1, 4. So the equation of this blue line is 4x plus y minus 8 is equals to 0. For the normal line, that is just y minus y sub o is equals to negative 1 over y prime o multiplied by x minus x sub o. So substituting the value of y prime o and also the value of x sub o and y sub o, and simplifying and rearranging, we can get the equation as x minus 4y plus 15 is equals to 0. So we were able to get the equation for the tangent and also the equation for the normal to this hyperbola at the point 1, 4. Now that we understand how to get the equation of the tangent and normal to a curve, now we can move forward to the angle between the two curves. So the angle between the two curves is defined as the angle of intersection, or the angle that is an acute angle of intersection of their tangent at the point of intersection. So it's equal to the angle of the intersection of their tangent. So say we have a curve which is denoted by this blue, a curve, and also the curve which is this red curve here. So we can see that the tangent at that particular point is this one. So we have the slope m1 and m2 for both the curves. So the angle is simply the angle between these two lines that are tangent to each curve respectively. So it can be solved by using the value of m1 and m2, or the slope of these tangent lines. So that is equals to tan theta is equals to m2 minus m1 over 1 plus m2 m1. So if we have the two equations, what we're going to do is to solve for the y prime, because that's just equals to the slope, and substitute that slope here and also the theta. Say for example, we have this. We have to find the acute angle between the curves x squared plus y squared is equals to 5x, and y squared is equals to 2x. So for x squared plus y squared is equals to 5x. So this is the equation. It is actually a circle, and this is the equation. And for y squared is equals to 2x, it is a parabola that is opening to the right with the vertex at 0, 0, because there's no value for hk. So this is the parabola, and then we have a circle. So it's important to recall your knowledge in analytic geometry so that you can create an illustration for you to be able to solve it easily. So the first solution would be to get the point of intersection of the two curves, because we are concerned with the acute angle is the acute angle that we can find at that point of intersection. So given the curve x squared plus y squared is equal to 5x and y squared is equal to 2x, we can substitute the second equation to the first. So our y squared is simply equals to 2x, and then solve for the value of x. So this equation will become the x squared plus 2x is equals to 5. This equation will become x squared is equals to 3x, because we will subtract 2x from 5x when we transfer it on the right side. And then we obtain x squared is equals to 3x, so that we can cancel out x and the x value would be equals to 3. So our value of x is equals to 3. So if x is equals to 3, then we can get also the value of y. So from y squared is equals to 2x, so from the second equation, we can also get the x in the first equation, but it's easier to use the second because it's more simple. So substituting the value of x is equals to 3, and then for the value of y, that will just be equal to the square root of 6, or simply positive negative 6 to the power of 1/2. So our ordered pair would be our x, which is 3, and then the positive 6 to the power of 1/2, and 3 minus 6 to the power of 1/2. So as you can see, there are 2 points of intersection based also in the result here. So now that we have the point of intersection, then we will solve for the first for the intersection x, which is equals to 3, and y positive 6 to the power of 1/2. So which is the upper one intersection. So for m1 from x squared plus y squared is equals to 5. So we will first get the equation of the tangent for the circle. So if we're going to draw it, so this is the tangent line to this point here at the circle. The tangent should touch that at one point. So if we're going to draw it, we will obtain this line here. So that is the first equation that we will obtain. So we can get that by deriving first the equation of the circle. So that is the x squared plus y squared is equals to 5. So that we will have 2x plus 2y prime is equals to 0. And then we get the y prime as negative 2x over 2y. So that our m1 is equals to the y prime, because it's equals to the slope of the tangent. So the m1 or the y prime is equals to negative 2x over 2y, where our x is the x of this point, which is equals to 3, and the y is the value y of this coordinate. So that is equals to 6 to the power of 1/2. So the slope of the tangent line at the first for the circle at the upper intersection is negative 1.22. So that's the value of m1. Solving for the intersection, same intersection now for the parabola, which is the y squared is equals to 2x. So we will first derive that and then get the value of y prime as 2 over 2y. Then we substitute the value of y, which is the same, 6 to the power of 1/2, so that we can obtain the value of the slope 2, which is the slope of the tangent at that particular point. So that's what we are solving. So the value of m2 is 0.41. So now that we have m1 and m2, we can finally substitute the values to our equation tan theta, which is equals to m2 minus m1 over 1 plus m2 multiplied to m1. Substituting the value, we can get the value of theta as 72.95 degrees. So if we're going to draw the tangent for the circle also, so the theta is the value between these two tangent line. So if you're going to look at it, it is symmetrical at the top and the bottom. So no need to solve for the bottom intersection. So the value of the acute angle is 72.95 degrees. So this is also there's also an angle here, but this is not an acute angle, as you can see. It's an obtuse angle. So we are just concerned with the acute angle. Now that we already reviewed how to get the angle between two curves, then we can proceed to the radius of the curvature. So the radius of curvature is defined as the center of the radius of the curvature of that curve. So say for example for the circle, so the radius is simply the radius of the circle. So that's the radius of curvature. But not all curves are circular. So that's why it's more convenient to use the general equation. The radius of curvature is equals to 1 plus y prime squared. All of this equation raised to the power of 3/2 over the absolute value of y prime prime. For the curvature, that is just the reciprocal of the radius of curvature. So let us have an example. Find the curvature of the curve xy is equals to 4 at 1/4. So performing implicit differentiation of the given equation, we can get y prime as negative y over x. So we can get the value of y prime by substituting the value x is equals to 1 and y is equals to 4. So our y prime is negative 4. So solving y prime prime, that is just the first derivative of the y prime. So our y prime is negative y over x. So our y prime prime is negative xy prime minus y over x squared. If you're going to look at it, it is just the quotient rule. So that's why we have this value. It's just the quotient rule. So now that we have the y prime and y prime prime, for the y prime prime, we will substitute the value of x, the y prime, and the y that you already obtained. So where x is equals to 1, y is equals to 4, y prime is negative 4. So that our y prime prime is equals to 8. So we can substitute all of this value now in the formula for the radius of curvature. The y prime, which is equals to negative 4, the y prime prime is equals to 8. So finally, we can get the radius of curvature as 8.76. So the radius of curvature is 8.76. For the curvature, that is equals to the reciprocal of 1 over the radius of curvature. And this is what we are looking for in this problem, the curvature. So the curvature is 0.1141. Now, let's proceed to maxima and minima. So the maxima and minima, as well as the inflection, are defined as follow in the table. So these are actually the different points on the curve. So for the maximum, the slope of the curve at the maximum is equals to 0. At the minimum of the curve is also equals to 0. However, at the inflection point, the slope is not equals to 0. The change of slope, or the y prime prime, for the maxima is a negative value. Because if you're going to look at, for example, this maxima here, so the maxima in a way is the maximum point in the curve. So it can be at a particular region. So here we have 3 maxima at that locals, and then the minima at that locals. So the maxima, if you're going to look at the change of the curve, it is actually decreasing. So that's why the change of slope, or the y prime prime, is negative for the maxima. For the minima, on the other hand, as the curve is has increasing value, the minima also increases. That's why the change of slope of the minima is positive. At the inflection point, the change of slope is equals to 0. For the maxima, the concavity is downward, as you can see here at this particular maxima. For example, that the concavity is downward. For the minima, the concavity is upward, as you can see. So all of the minima has an upward concavity. So if you have those values, you can actually trace a given curve and predict its behavior. Okay, let us have an example. Given the curve y is equals to x cubed minus 3x squared minus 9x plus 10. So we are going to find the maximum point, the minimum point, and the point of inflection. So you can actually get a shortcut solution by using this MOS. Unfortunately, we cannot use that in the board exam, so that's the reason why we will have to use the formula. So first, we are going to solve for the y prime. So the y prime for the given equation is 3x squared minus 6x minus y. So it's important to get the y prime because we will equate it to 0 because we know that when y prime is equals to 0, or when the slope is 0 because y prime is 0, we can get the value of the maxima and the minima, right? Because at the maxima, the slope is equals to 0 also for the minima. So the slope at that particular point is 0, meaning it's horizontal. So the tangent line at that point is horizontal. So we will equate the y prime to 0 and then solve for the value of x. So solving for the value of x, we can obtain two values, which are 3 and negative 1. So meaning, we will also be able to get two values for y. When we substitute back this equation at this value of x and negative 3 and negative 1 to the given equation, we can get the value y. So at x equals to 3, our y is equals to negative 17. And at x is equals to, so our first point, as you can see also here in our decimal solution, is 3 negative 17. So that is the first point, or that is the first critical point. At x equals to negative 1, when we substitute the value x negative 1 to the given equation, we can get the y as 15. That's why you can also see here that the ordered pair would be negative 1, 15. So this now represents the extreme positions, or the maximum or minimum point. But if you do not have this MOS, you cannot yet know whether it's the maxima or the minima. So what we can do is to first solve for the y prime prime, so that we will be able to determine if it is a negative value or a positive value, because we know that if it is a negative value, so if the change of the slope is a negative, it is the maximum. But if it is a positive value, the point is a minimum. So for the y prime prime of the y prime, that would be equal to 6x minus 6. So at the first point, which is 3 negative 17, the y prime prime is 12. We just simply substitute the value of x. So if you're going to look at it, the y prime prime is a positive value. So therefore, it's a minima because the change of the slope is a positive. So the minima is the 3 negative 17. At the second point, which is negative 1, 15, we substitute the value of x, which is negative 1. The y prime prime is negative 12. That means that the change of the slope is decreasing. So that point is a maxima. So our maxima is negative 1, 15. So we're able to solve the minima and the maxima. So we will just solve for the point of inflection. So the point of inflection can be solved by equating y prime prime equal to 0 and solving for the ordered pair. So our y prime prime is 6x minus 6. We equate it to 0 and obtain the value of x equals to 1. At x equals to 1, we can get the value of y from the given equation. So that is negative 1. Therefore, our point of inflection is the ordered pair 1, negative 1. So in this way, we can trace the curve without necessarily using the Dismos app. So we trace the minima at 3 negative 17 and the maxima at negative 1, 15, and the point of inflection is 1, negative 1. We also have applications of maxima and minima in worded problems. So in solving maxima and minima worded problems, these are the recommended steps. So first, we make an equation that is to be maximized or to minimize. The second is, if the right side of the equation has two or more variables, then we have to convert it to one variable only. Then we differentiate the equation with respect to the chosen variable in the right side. And to maximize or minimize, we know that we have to equate it to 0 and solve for the unknown. Sample problem number 18. Find the height of the solid right circular cylinder of maximum volume that can be cut from a spherical wood of radius 8 inches. So this is the illustration. We have a spherical wood, the blue one. The radius of this sphere is 8 inches. Then we're looking for the height of this cylinder that you can see here that we can cut from this sphere. So if we're going to examine this cylinder, we can at the cross section we can actually create this figure wherein the half the height of the cylinder as well as the radius of the cylinder and the radius of the sphere will actually form a triangle. We have to obtain that in order to get the relationship between the radius of the sphere, which is the big letter R, the radius of the cylinder, which is small r, the h over 2, which is half the height of the cylinder, which is what we are looking for. So the height of the solid right circular cylinder of maximum volume. So we can make an equation that is to be maximized or minimized. Examining the given problem, we are looking for the maximum volume of the solid right circular cylinder. So therefore, the equation is the equation for the right circular cylinder, and that is the volume for the right circular cylinder, which is pi r squared h. Since the right side of the equation has two variables, which are the radius and the height, then we have to convert it to one variable only. So by using Pythagorean relation in the given figure that we have obtained, so we will get r squared is equals to big R squared minus h squared over 4. Then, if you're going to substitute that r squared to this volume of the cylinder, then we will obtain this equation pi h r squared minus pi h cubed over 4. So now that the right side has only one variable, which is the h, take note that the big letter r is not a variable because it's a constant. It's equals to 8 inches. But h has no value yet, so that is a variable. So we differentiate the equation with respect to the chosen variable in the right side, which is the height. So by differentiating with respect to height, the volume of the cylinder will be equals to pi r squared minus pi 3h squared over 4. Now after differentiating it, we can maximize or minimize it already by equating the equation that we have obtained to 0 and solve for the unknown. So equating to the 0 and solving for the value of h, which is the unknown, our h is just equal to the square root of 4r squared over 3. And since r is equal to 8 inches, then the height of the right circular cylinder of maximum volume that we can cut from this spherical wood is 9.24 inch. So therefore, you can cut a height of 9.24 inch a cylinder if you have that 8 inches of a sphere. Let's proceed to time rates. So for time rates, here are the suggested steps in solving. So make an equation based on the given situation. If the right side of the equation has two or more variables, and if the rate of change of the other variable are not given, then converting it to one variable should be necessary. Differentiate it with respect to time because this is a time rate. Then substitute the boundary conditions and solve for the unknown. Say for example, you have a water flowing in at a rate of 12 meter cube per minute into a conical tank of 10 meter diameter on top and 20 meter deep. We are going to solve how fast in meter per minute the water surface rising when the depth of the water in the tank is 8 meter. So this is the illustration. So we have the conical tank. So the diameter at the top is 10 meters, so the radius is 5. And the height is 20 meters because it's 20 meter deep. So water is flowing into the tank, and that is equals to the change in volume of the water in the tank. So that's why it's the dVdt, or the volume of the water in the tank is changing with respect to time, and the value is 12 meter cube per minute. So you can also see that the meter cube is a volume and the minute is a time. So that's why the dV/dt is 12 meter cube per minute entering into this conical tank. And if you're going to have a relationship, the change of the radius of the water when the height is rising is also illustrated here. So the dy/dt on the other hand is the what we are looking for, or how fast the water surface is rising. So that is the dy/dt, and that is what we are looking for. So the dy/dt. So take note that the radius will differ depending on the height. So say for example here the radius would be like this, but if the water is in this level, the radius would be greater, and then in such a way that if it is full, then it will be 5 meter. So it's actually increasing. So the first step is to make an equation based on the given situation. So we are given here with a conical tank. So we will start first with the volume of that conical tank. And we know that the volume of the cone is 1/3 pi r squared h. So if you're going to look at it, the right side of the equation has 2 or more variables. So we have to change that variable with respect into another one so that we will get a single variable equation. So by ratio and proportion, if you're going to examine this triangle and also this triangle here, by ratio and proportion, we will have our 20, which is this height, over the 5, which is the radius of this bigger triangle, is equals to the height of this smaller triangle divided by the radius, which is this one. So we simply have the ratio and proportion of these two triangles to get the relationship of the height and the radius. So that the radius is equals to height over 4. So therefore, if the height is given as h, then the radius would be 1/4 of the height always. So by substitution to the equation for the volume of the cone, then we can obtain this one. So that is our 1/3 pi r squared, since our r is already h over 4, multiplied by the height, so that this equation will become 1/48 pi h cubed. So now it's already a single variable. Then we can differentiate it with respect to time. So take note, do not differentiate when it is not yet a single variable equation. So by differentiating with respect to time, we will obtain this one. So we have 3/48 pi h squared dh over dt. So we differentiate the height with respect to time. That's why we have dh over. We multiply with the dh dt here. And then we substitute the boundary conditions. We know that the change of the volume, which is the dV/dt, is equals to 12 meter cube per minute. We equate that with the dV/dt that we obtain. So when the height is 8 meter, we can obtain the value of the dH/dt. So the dH/dt, so this one, is 12 meter cube divided by 3/48 pi h squared. So when the height of the water of the tank is 8 meter, then the water is rising at a rate of 0.9549 meter per minute. And that is the dy/dt also. So that's the dH/dt, or the how fast the water surface is rising when the height is 8 meter. So finally, the differentials. So the differentials are helpful in solving error problems in experiment, for example, or in measurement, where the dr over r is the relative error in the radius, for example, if we are measuring the radius. And if we're looking for the area, the error in the area is dA over A. The relative error, on the other hand, for the volume, if we are looking for the volume, is dV over V. We can also use this for mass and other quantities. So that is how we can use the differentials in error problems. So the error are defined as the the differential divided by the quantity that we are measuring. So what is the allowable error in measuring the edge of a cube that is intended to hold 8 meter cube if the error of the computed volume is not to exceed 0.03 meter cube? So let us put the allowable error in the edge of the cube to be dA, because the edge of the cube is A. So the allowable error would be the dA. The volume of the cube is defined as a cube, and it's also given in the problem as 8 meter cube. So we can get the value of A as 2 meter by taking the cube root of 8. So the edge of this cube is 2 meter. So we differentiate also this volume so that we can obtain 3a squared dA. So we put the dA here because this is what we are looking for. It's the allowable error in the edge of the cube. So our dV is equals to 3a squared 3a squared dA. And then our a squared is equals to 2 meter, and our dA is not yet known. So that we know that the error of the computed volume is not to exceed 0.03 meter cube. So that's why we have to equate the value of dV as 0.03 meter cube, because it's the error of the computed volume. Thus, our dA, which is what we are looking for, the allowable error in the edge, is the dV over 3a squared. So dA is 0.0025 meter. So that is the allowable error in measuring the edge of the cube. Now that we're done with differential calculus, let's move forward to integral calculus. On this topic, we will be discussing the various subtopics, beginning with integration. The study of integral calculus consists in developing techniques for the determination of the integral of a given function. This subject finds extensive applications in geometry, natural, and social sciences. This course covers the applications of integral calculus to the determination of plane areas, length of arcs, volumes and surfaces of solids in revolution, center of gravity, and moment of inertia. Integration is a process which is the inverse of differentiation. It is a process of finding the integral of a function. If d over dx of the function of x is equal to f of x, we say that f of x is an integral or a primitive or antiderivative of f of x. To integrate means to find the integral of f of x, and function to be the integrated is called the integrand. Say for example here, the dx indicates that the integration is to be performed with respect to x. So x there is the variable of integration. The integration of a function is unique because by assigning different values to c, we can get several integrals of f of x. F of x plus c is called the general integral of the indefinite integral of a function. The fundamental rules for integration. Rule number 1. The integral of the product of a constant and a function is equal to the product of the constant and the integral of the function. Rule number 2. The integral of the algebraic sum of two or more functions is equal to the algebraic sum or difference of the integrals of those functions. Integration formula. So here are some of the integration formula that are frequently used in integral calculus. What is the integral of 3x minus 1 cube dx? By applying substitution, we will notice that if we let u is equal to 3x minus 1, or the function inside the quantity here that is raised to the power of 3, our du will be equal to the 3 dx. Thus, our dx will be, in terms of u, will be equals to 3 du. 1/3 of du rather. 1/3 of du. So this dx here will also be replaced by 1/3 du. That's why we have here du over 3 multiplied by the u cube. Then we notice that we can take out the constant 1/3 because of our basic rule that if we have a constant, we can just multiply that constant with the integral of the function that we are integrating. So that's why we have here 1/3 multiplied by u cube du. Then since we have here a power function, then we can use the power rule. So in the power rule, for example, of the variable x, we can get the result using this formula. So we just simply add plus 1 to the power of 3 over 3 plus 1. And then we substitute back the value of u, since our result should be fine in terms of x, where u is equal to 3x minus 1 from the beginning, such that we will have this. Then we will simplify. And once you're done with simplification, then we will obtain 1 over 12, 3x minus 1 to the power of 4 plus c. What is the integral of x multiplied by cosine 2x squared plus 7 dx? So if you find here, we have two functions x and the function cosine of 2x squared plus 7. So what we can do first is to let u equals 2x squared plus 7. So we let this function inside cosine as our u. Then if we differentiate that, our du will become 4x dx, so that our x dx is equals to du over 4. So if x dx is equals to du over 4, this x multiplied by dx here can be reduced to du over 4, so that we will have cosine of u du over 4. Then we can take out the constant 1/4 and multiply it with cosine of u du. So the integral of cosine of u is 1/4 sine u plus c. And we substitute back u, which is 2x squared plus 7, so that we will obtain our final result, which is 1/4 sine 2x squared plus 7 plus c. What is the integral of cosine x plus 2 over x minus ex plus ex dx? Applying the sum rule that if we have several functions, we can simply take out the integral of each term separately. Since we have here 3 terms, cosine x, 2 over x, and ex, then we can integrate each of the terms separately. So this is the integral of the first term plus the integral of the second term minus the integral of the third term. So for the first term, the integral of cosine is sine. For the second term, the integral of that is, since we have a constant 2, we can take that out and take the integral of dx over x, which is ln x. So that's why we have 2 ln x. For ex, it's still ex. Substituting back those results, then we can get the integral as sine x plus 2 ln x minus ex. And adding the constant to the solution, we will have sine x plus 2 ln x minus ex plus c. What is the integral of cosine x minus sine x over cosine x plus sine x multiplied by 1 plus sine 2x dx? So this is our given. So using identity, so that we can reduce this equation first before we integrate, our 1 is equals to cosine squared x plus sine x. So we can substitute the value of our identity to the value of 1 in the equation, so that we will have this part in substituting for 1. If you're going to look at it, this will become a perfect square binomial. So that's why we can replace this instead with cosine x plus sine x squared. Then we can cancel out the cosine x plus sine x here, and this one will become a power of 1. So that's why we have this multiplied by the cosine x minus sine x. Multiplying the two, we will have cosine squared x minus sine squared x dx. And they are equal to, this equation is equal to cosine 2x dx. So for that equation, we would let u is equals to dx, and our du will become 2 dx, so that dx is du over 2. So our equation will become cosine u du over 2. We take out the constant 1/2 and take the integral of cosine u du, and that is 1/2 sine u plus c. So putting back u, which is 2x, our equation will become 1/2 sine 2x plus c. So aside from the basic formula, we also have some formula here that are for advanced. We have the inverse trigonometric functions. So these are the integral formula involving inverse trigonometric functions. So we have arcsine, arctan, arcsec here. So let us have an example of the application of that. What is the integral of dx over 3x squared plus 1? So noticing our given can be solved using the integral of using the arc inverse of tan formula, which is given as this one because of the plus sign. So we have the plus sign also here. So based on that pattern, which is the dx over 3x squared plus 1, our a squared is equals to 3x squared, so that the value of a is just the square root of 3 over x. Our u, on the other hand, is just equals to 1. So we put that value here in that pattern, so that we will have 1 over square root of 3x arctan of 1 over square root of 3x. So, and that is our answer. Integration techniques. We have different techniques that we can use in integration. Actually, we also use this already. First is the integration by substitution. So the general forms for integration by substitution are given here. So say for example, our form is in the form f prime x dx over f of x. That can simply be written as log of f of x, since our denominator is the antiderivative of the numerator. For the second form, we have f of x to the power of n f prime x dx. We can write that in the form f of x n plus 1 over n plus 1, because if you can notice, this function here is just the this function is just the first derivative of the given function being raised to the power of n. And then we have ex plus b, that can be written as ex plus b over a. So if you have a function, the constant can simply become the denominator. Then we will have the function ex plus b in the numerator. So what is the integral of x squared over 1 plus x cubed? So if you can notice, this function is in the form f prime u du over f of u, because which is equals to log f of u, because you can see that our denominator is just the first derivative of the numerator. The numerator rather is the first derivative of the denominator. Our derivative of 1 plus x cubed is x squared, but we just multiply it with a constant 3. So what will happen is, if our f of u is equals to 1 plus x cubed, then our f prime u will become 3x squared dx. And our dx will then become f prime u du over 3x squared by rearranging this form. Substituting our x squared over 1 plus x cubed dx, the integral of that will just simply become x squared over u multiplied by f prime u du over 3x squared. And this form is can be reduced further to this form by cancelling out the x squared. And then we can take out the constant 1/3, so that what is left is the f prime u du over f of u. Then this form is just equals to log of f of u multiplied by 1/3. Putting back the function of u, which is 1 plus x cubed, our final result will become 1/3 log 1 plus x cubed plus c. What is the integral of arctan x cubed over 1 plus x squared? So using the form this one, which is equals to this one, so it's like a power formula or a power rule, because if you're going to look at it, the derivative of our arctan of x is just equals to the value, which is 1 over x squared, 1 over 1 plus x squared. So if we let f of u equals arctan of x, then our f prime u, so you notice that what we left as f of u is the function that is being raised to the power of n, and this is the arctan x. So our f prime u du will become dx over 1 plus x squared. So our dx is just 1 plus x squared multiplied by f prime u du. So substituting, we can, our 1 plus this equation will become f of u cubed over 1 plus x squared multiplied by 1 plus x squared f prime u du. Then we can cancel out the 1 plus x squared here and 1 plus x squared here. So this will be, and we can have this result then. Finally, this can be integrated now since it is in the form that is here. So it will become f prime u 3 plus 1 over 3 plus 1, and putting back f of u, which is arctan x, then our result will become arctan x to the power of 4 over 4 plus c. What is the integral of cosine x multiplied by cosine 2x dx? So applying integration by parts, putting u is equals to 2x and our v prime as cosine x. So looking at it, our integration by parts is simply u v. So our u is cosine x, that's why cosine 2x, that's why we have here cosine 2x multiplied by v. So v is the integral of cosine x, which is sine x, that's why we have sine x here, minus the integral of v du. So our v is sine x, and our derivative of u is the derivative of cosine 2x, that's why we have here minus 2 sine x, sine 2x dx. So for the integral of this part, the integral of negative 2 sine 2x sine x dx, that is simply negative 4 over 3 sine cube x. So that the second term here will become this one. So simplifying the result and adding constant to the solution, we will have cosine 2x sine x plus 4 over 3 sine cube x plus c. Another integration technique is the integration by substitution. So when the following integral appears in the equation, we can use the following substitution. What is the integral of dx over square root of 9 minus x squared? So using the trigonometric substitution, x equals 3 sine x, 3 sine theta, since the form a minus x squared appear in the equation, then our dx will become 3 cosine theta d theta. So we can replace the value of x here with this 3 cosine theta d theta. That's why we have here dx is equals to 3 cosine theta d theta, and the value of x as the 3 sine theta. So simplifying, we will have this one. So 3 squared is 9 sine squared theta. And then we can take out the square root of 9. That's why we have 3 here. And cancel out that 3. And also for the square root of 1 minus sine squared x, that is simply cosine theta. We can cancel out 3 cosine theta, which appears both in the numerator and denominator, so that we will have the integral of d theta. So the integral of d theta is simply theta. That's why we have here theta plus c. And going back to our given, our theta is simply x, the arcsine of x over 3. So that's why we have arcsine x over 3 plus c. Then another technique is the trigonometric transformation. So we have here the different forms of integral sine m x cosine n x dx, the integral of sine m x dx, or the integral of cosine n x dx. We have two cases here. If at least one of m or n is odd number, or both m and n is odd, then we let sine squared x is equals to 1 minus cosine squared x, or cosine squared x equals to 1 minus sine squared x. We can transform the trigonometric functions with the odd power. For case 2, where both m and n are odd, then we can use this following trigonometric transformation. Say for example, we have what is the integral of sine cube x cosine squared x dx. We can transform the function with the odd power using sine squared x is equals to 1 minus cosine squared x. Since m is odd and n is uneven. So transforming the sine squared x, it will become 1 minus cosine squared x. Then we multiply it with cosine squared x, sine x dx. Then distributing the cosine squared x sine x, we will have cosine squared x sine x dx minus cosine to the power x sine x dx. The integral of the first part here is, since the derivative of cosine is sine x dx, then we can use the power rule so that it will become negative cosine cube x over 3. For the second term, same also, we can use the power rule because the derivative of cosine is sine. Then we will have cosine to the power 5x over 5 plus c. Trigonometric transformation for tan to the power of n x and sec to the power of n x. So we can use the following transformations. What is the integral of tan cube x dx? We apply substitution where u is equals to secant x. So our equation will become negative 1 plus u squared over u. So we expand the negative 1 plus u squared over u. It will become negative 1 over u plus u. Then this will become negative 1 over u plus u du. So we apply the sum rule. We integrate each of the term. So that the integral of 1 over u du is ln u. For the integral of u du is just u squared over u. Then it will become negative ln u plus u squared over 2. So we put back a secant x. And applying the constant to the solution, we will get negative ln sec x plus secant squared x over 2 plus c. So integration by parts. So again, the integral of u dv is simply uv minus integral of v du. We actually used this in the previous solution already. So let us have another example of that. So what is the integral of x sine x dx? So applying integration by parts, we can let u is equals to x and v prime is equals to sine x. So we will have our u is equals to x, then our v is the negative of cosine x, that's why we have negative x cosine x here, minus v du. Our v is negative cosine x and the derivative of u is dx. So for the negative cosine x dx, it will become negative sine x, so that it will become like this. And simplifying it, we will get negative cosine x plus sine x plus c. What is the integral of log x dx? Applying integration by parts, we will let u is equals to ln x and v prime is equals to 1. So our u times v is x ln x and our v du will become dx. Simplifying, we will get x ln x minus x plus c. Integration by partial fraction. So the degree of the numerator of the given fraction should be less than the degree of the denominator. If so, it must be done by division. The terms of 2 or more in the denominator of the fraction should be resolved in 2 possible real linear factors. Denominator with distinct linear factors will be reduced into this way, with this form. Meaning, if each of these factors of the denominator is distinct, they are different, then we can reduce it into this form. We solve for the value of a, b, c and integrate each term. Denominator with repeated factors will become like this. So first we are going to for the repeating part, which is x plus a to the power of r, so we will write that in the form x plus a, then the constant here will become a sub 1 plus a sub 2 over x plus a to the power of r, until such time that we will obtain the power. So if it is to the power of 3, then we will have 3a1, a2 and a3 plus b dx x plus b. So we will solve for a, b, and c and integrate each of the term separately. If we have a denominator with biquadratic factor, then our equation will become x over will become in this form here. So we have x plus a multiplied by x squared plus b squared. So this is a biquadratic factor. So we can have the partial fraction as a dx over x plus a plus the integral of bx plus c dx over x squared plus b. So we will have for the quadratic factor, its numerator will have the constant bx, b multiplied by x plus the constant c. Then we solve for the value of a, b, and c and integrate each term. So we have then what is the integral of x dx over x minus 1 squared and x plus 2. So take the partial fraction first of x over x minus 1 squared multiplied by x plus 2. Its partial fraction, if you can still recall your knowledge on partial fraction, so we can also find here that we will have the 3 terms representing first the x plus 2. So we have here the x plus 2, and then we have the x minus 1 and the x minus 1 squared, wherein the repeating part is also repeated, but its power is also increased. So this constant negative 2 over 9, positive 2 over 9, and 1/3 is derived using partial fraction decomposition. So you can review that in order to get that constant. So since you already have the partial fraction, then we can integrate each term separately by applying the sum rule. So we have the integral of the first term plus the integral of the second term and finally the integral of the third term. So integrating for the first term, we will get For this term, it will become 2 over 9 ln x plus 2. For the second term, this will become 2 over 9 ln x minus 1. And for the third term, it will become negative 1/3 x minus 1. So putting out all of this in the original formula, then we will get this one, and applying constant at the solution, it will become negative 2 over 9 ln x plus 2 plus 2 over 9 ln x minus 1 minus 1 over 3 x minus 1 plus c. The Wallis formula. So if you have an equation, the integral of an equation sine m x cosine n x dx, integrating it from 0 to pi over 2, then we can actually have a shortcut solution in this form. So all we have to do is to multiply the power of m minus 1, so on and so forth, and also n minus 1, so on and so forth, over m plus 1, and also for m plus n. Multiply it by a if both m and n are even, and 1 if otherwise. For example, we have the integral of 12 sine to the power of 5x cosine m to the power cosine 5x dx, integrating it from 0 to pi over 2. Then we can use the Wallis formula. Since if m and n are both even, then we can have a is equals to pi over 2. Otherwise, we will let a is equals to 1. Since the power m and n are odd, then we will use a is equals to 1. That's why we have here 1. For the value of m, we will deduct 1. So we'll have 5 minus 1. Then we multiply it with 5 minus 3. Same also with the other function, with other power, which is 5. We'll also do that. And for the denominator, we will have the sum of 5 plus 5, we'll have 10, and we decrease it by 2 until such time that the least will become 2. So 10, 8, 6, 4, 2. So that's why we have 0.0167 here. So you can also hear that the least here is also 2 or 1. So 5 minus 3 is 2. Same also here, it's 2. So finding areas using integration. In finding areas using integration, we will use this formula if they are in the rectangular coordinates, meaning xy plane. Using a vertical differential strip, our area is simply the integral of y dx. So the y represents the length and dx as the width. If we have a horizontal differential strip, we will have the integral of x dy, where x is the length, dy is the width. What is the area bounded by the curve y squared is equals to x and the line x minus 4 is equals to 0? Our first equation is y squared is equals to x, and the second equation is x minus 4, or x is equals to 4. So if we graph this function, our y squared is equals to x is a parabola, represented by this parabola here, and our x equals to 4 is a straight vertical line, represented by this line. So first, we will get the intersection of this parabola and this line. So we can substitute equation 2 in equation 1. That's why we have here y squared is equals to 4, because x is equals to 4. And finally, our y is positive negative 2. So the coordinate of this point, the intersection, is 4, 2, and 4, negative 2. So we can integrate it now by using a vertical strip. So if we will use a vertical strip, our length is y and our width is dx. As a consequence, we will have the area as y dx. Then we are going to run the strip from 0, x equals to 0, to x equals to 4. That's why we have here 0 to 4. And since there are two parts here, we have the upper part of this parabola and the lower part, they are symmetric. That's why we multiply it by 2. Substituting the value of y from our given equation, it is the square root of x. So from this, y is square root of x. That's why we have 2 times the integral of square root of x dx from 0 to 2. From 0 to 4 rather. So in this part, you can actually use already your scientific calculator. But if you want to do the manual integration, then you will have this one. So the result will be 32 over 3 square units. If we have polar coordinates, then our area will become 1/2 the integral of r squared d theta. So we have, what is the area bounded by the curve r is equals to 8 cosine 2 theta? This is actually a 4 rows curve, polar curve. So our area is 1/2 r squared d theta. And then our r is equals to 8 cosine 2 theta. That's why we have this part here. Evaluating from 0 is equals to theta to theta is equals to 360, meaning it's from the beginning till the end, or 2 pi. So that's why we have 1/2 multiplied by 8 cosine 2 theta squared d theta from 0 to 2 pi. Then the area bounded by the curve is 32 pi unit square. Finding centroid using integration. The centroid is the center of mass of a given figure. Say, for example, you have here this given figure. Its centroid is represented by x bar and y bar. Its coordinate, the coordinate of this centroid, or the center of this graph, is x bar, y bar. For the x bar, it is the integral of x dA over a. For the y bar, it's the integral of y over 2 dA over a. So it's y over 2 because the center of this strip here is at y over 2 from the reference axis, which is the x-axis. For the y, its distance from the reference axis is y. That's why we have, for the x, it's x. As you can see here, its distance from the reference axis is x. That's why it's x. Locate the centroid of the plane area bounded by the equation y squared is equals to 4x, x is equals to 1, and the x-axis on the first quadrant. We have 3 equations. We have that y squared is equals to 4x, the x equals to 1, and the x-axis on the first quadrant. So graphing it, we'll have a parabola, this vertical line here, which is the x plus 1, and the x-axis on the first quadrant. So we are referring to this black shaded region here. So we would like to get the centroid of that area. Using a vertical strip, we have here this vertical strip with the length y and with dx. And finding first the intersection of the line and the curve so that we will know the beginning, the end of the integration. At x equals to 1, the value of y is positive negative 2. So that's why the intersection is 1/2, 1, 2, and 1, negative 2. Solving for the area of this portion here. So the area of a parabola is simply 2/3 base times height. But since we are just looking for half of this area, so that's why we have 1/2, 2/3 base times height. The base is equals to 4 because the value of the from this point, from this point rather, from point to point is 4, and then the distance from this base here is 1. This height here is 1, and this base is 4. That's why we have here 4 and 1. So the area is 4 over 3. From our formula, our ax bar is equals to y dx multiplied by x from 0 to 1. Our y is simply 2 square root of x, because if we get from y squared is equals to 4x, it will just become 2 square root of x. We multiply it with dx and x. So if we integrate this, we will get the result x bar as 3, 5. We can also do the same for y bar, taking note that our y, the distance of y from the x-axis is y over 2. That's why we have here y over 2. So solving also for that one, you can actually use the calculator already. Our y bar is 3/4. Thus the center is at 3, 5, 3, 5, 3/4. Finding arc length using integration. So these are the general formula that we can use for finding arc length using integration. Find the length of the arc of the parabola x squared is equals to 4y from x equals to -2 to x equals to 2. Our formula is the integral of 1 plus y prime squared dx from x1 to x2. Given is x squared is equals to 4y. So the d over dx of x squared equals to 4y is 2x equals to 4y prime. So our y prime is simply 1/2 x by implicit differentiation. From x equals to -2 to x equals to 2, so we substitute that lower and upper bound here, and we integrate this part using calculator. Our s, or the length of the arc, is 4.59. Finding the surface area using integration. The first approach is the proposition of Pappus, wherein we have a curve and we rotate it with respect to an axis, and the center is denoted by d prime. The distance from the center to the axis of rotation is d prime. Then our area, surface area, is the length of the arc, so the length of this arc multiplied by 2 pi d prime, or d bar. Find the area, or surface area, generated by rotating the parabola arc y is equals to x squared about the y-axis from x equals to 0 to x equals to 1. So by graphing, we will obtain this. Y is equals to x squared, it's the parabola, when x equals to 1, and y is equals to 1. So the value of y is equals to 1 when x is equals to 1, based on this equation. So using the proposition of Pappus, our formula will then become the ds multiplied by 2 pi d. For the length of the arc, it is square root of 1 plus dy over dx squared dx multiplied by 2 pi x, because the distance from the centroid, so the center to the curve, is equals to x. So the distance is equals to x. So the distance from this point, for example, if you are looking, is just equals to x. So when y is equals to x squared, dy is equals to 2x dx, and dy over dx is equals to 2x. So that dy over dx squared is equals to 4x. So we substitute the result here so that we obtain this one. So from this, you can already use the scientific calculator, and we can find that the surface area is 5.33 square units. Finding volume using integration. For the volume, we will use the second proposition of Pappus, that the volume is just equals to the integral of the differential area multiplied by 2 pi d bar. The area is the area of the cross-section that we revolve, and d bar is the distance from the centroid to the axis of rotation. Given the area in the first quadrant bounded by x squared is equals to 8y, the line y minus 2 is equals to 0, And the y-axis, what is the volume generated when the area is revolved about the line y minus 2 is equals to 0. From our given, which is x squared is equals to 8y, when y is equals to 2, our value of x is positive negative 4. So we can graph the parabola, which is x squared minus 8, and then the intersection of this parabola to the line y minus 2, which is this line here, is our value positive negative 4. So that's why the coordinate of the intersection is negative 4, 2, and positive 4, 2. And we are just concerned with the first quadrant, so we will analyze the first quadrant here. So we will get the volume that can be generated when we revolve this line, this area rather, with respect to this line, which is y minus 2 is equals to 0. If we're going to revolve this line, this strip, with respect to this line, it will have a dist. We will be able to create a dist with the radius y and thickness dx. So for a dist, its volume is pi r squared. So the volume can be written as pi, the radius which is y squared, the thickness which is dx. So that's why we have this pi y squared dx. From 0 to 4, because our concern is just in the first quadrant, beginning from 0 to the intersection here, which is x equals to 4. For the value of y, it is the value y here, the length of the strip, and that is the y up minus y down. Y up is the y of the line, which is equals to 2, and y down is the curve here. So it touched the curve here at the bottom. That's why we have the y down is x squared divided by 8 if we resolve for y here. That's why we have here x squared over 8. Then we raise this to square dx. So from this, you can already use the calculator to get the result, but you can also solve it manually, just like here. So the volume that you will obtain is 26.808 cubic units. Another method in finding the volume is using a circular dist method. So actually, we already have this in the previous example, because the first one is a more general approach. So we still have the same problem, and we're going to use the dist method. You can see that we will also obtain the same result. Then we have the shell method. For the shell method is where we will use the shell method if the volume that we will be able to form when we rotate the strip is a hollow cylindrical shell. Say for example this one, if we rotate the strip, you can see that we will be able to create a hollow cylindrical shell with a thickness of dx, with a radius of x, and with a length of y. So the volume of this shell now will become 2 pi y x dx. So the length, the width, and the height. The area bounded by the curve y squared is equal to 12x and the line x equals to 3 is revolved about the line x equals to 3. What is the volume generated? So we have the line, the curve parabola y squared is equal to 12x, and the line is equal to x equals to 3. The point of intersection is also can be found. If we're going to revolve the strip here with respect to the line x equals to 3, you can see that we will be able to create a shell. So this shell with a thickness of dx, radius of 3 minus x, and the length of y. So using the shell method, substituting those values in our formula, then we will have 2 multiplied by 2 pi, 3 minus xy dx from 0 to 3. So from this, you can already use calculator, but you may also opt the manual method here. You will still obtain the same result, which is 180.955 cubic units. Then we have the ring method. So we'll use this formula if the volume that we will generate is a ring. A ring with a radius of x sub 1 and x sub 2, and the thickness is dy. We have the given area in the first quadrant bounded by x squared equals to 8y, the line x equals to 4, and the x-axis And we're going to get the volume generated by revolving the area about the y-axis. So we have this form here. We have the parabola, the line x equals to 4. And we are looking for this the volume that can be generated when we revolve this area, and the line x is equals to at the y-axis rather. So if we revolve this area in this strip in the y-axis, we can find that we'll be able to generate a ring. So that's why we will use the formula for the ring method. The x left is simply the line x equals to 4. The x right is the curve, which is square root of 8y. That's why we have our x squared is equals to 4 squared. Our x right is equals to the square root of 8y squared dy. So we integrate it from 0 to 2, since we will run the strip from this line to this point here, 0 to 2. So from this, you can either use calculator or you may opt to use manual method. So our volume is 50.265 cubic units. Finding work using integration. Work is defined as the force multiplied by the distance traversed. If the applied force varies with the distance, then the best solution is to apply integration. An application of this is in the Hooke's law, where work is defined as a force multiplied by a distance traversed. If the applied force varies with the distance, then the best solution here is to apply the integration. A hemispherical tank of radius 6 feet is filled with water to the depth of 4 feet. Find the work done in pumping the water to the top of the tank. How about when the tank is full? So this is the illustration of this hemispherical tank of radius 6 feet. You can see that the radius here is 6 feet, and it is filled with water to a depth of 4 feet. So the water level here is 4 feet. So we are looking for the work done in pumping this volume of water to the top of the tank. The distance from the surface to the top of the tank is 6 minus y. So this is the distance that we are going to pump the water. The work is known as force times distance. So the differential work is the differential force multiplied by the distance. The distance here is the distance that we are going to move the water. So that is the 6 minus y. So that's why we have here 6 minus y. The force is equal to the weight of the water, because this is the force that will oppose the pumping. Force is known as mass times gravity, and mass is density times volume. The differential force then will become density times gravity times differential volume, where dV is the differential volume of the water. From this figure, this is the volume of the water that we are to take out from the tank. So the volume of that water is simply pi x squared dy. By Pythagorean relationship of our drawing, we can get a relationship that x squared is equal to 6 squared minus 6 minus y squared, or 36 minus 6 minus y squared. So our dV will become pi x squared dy, or pi 36 minus 6y squared dy. Thus, the differential force is rho g pi 36 minus 6 minus y squared dy. Then our work is the differential force multiplied by 6 minus y. So putting those value, our differential work will become this. And then we are going to simplify and substitute the value. So the value of density, gravity, and then we have to convert the pound force to we have to convert this pound mass feet per second squared to pound force, multiplied by pi minus 6 minus y, and this term times dy, and integrating these values from 0 to 4, since we are to take out the water from the height 0 to height 4. So the work is 50,185.06 pound force feet, and converting it to ton, it is 25.09 feet tan. Finding the moment of inertia using integration. It is a rotating body's resistance to angular acceleration or deceleration equal to the product of the mass and the square of its perpendicular distance from the axis of rotation. So for example, for this figure, the moment of inertia with respect to the line x is the integral of dA multiplied by y squared. For in the moment of inertia with respect to the y-axis, you can see that the centroid is half. That's why we have here x over 2 squared. So find the moment of inertia with respect to the x-axis of the area bounded by the parabola y squared is equals to 4x and the line x equals to 1. When y squared is equals to 4x at x equals to 1, or x equals to positive negative 2. Thus, the parabola and the line intersect at points 1, 2, and negative 1, negative 2. So this is how the drawing would look like. So we are concerned with the moment of inertia with respect to the x-axis. So this is the x-axis, and we can see that the distance of the strip is y from the x-axis. Thus, the moment of inertia is y squared dA multiplied by 2, since we have the upper and the lower portion. For the value of dA, it is simply the area of the strip, which is x dy. And x is the x left minus x right based on the figure. Substituting the value of x left, which is 1, x right is equals to y squared over 4. So this part, we can already use the calculator to get the value. So the moment of inertia with respect to the x-axis is 2.13. Multiple integral. An integral in which the integrand is integrated twice is a double integral, denoted by this notation here. An integral in which the integrand is integrated twice is a triple integral, denoted by this notation here. Evaluate the integral of this function here. We can actually integrate each part and multiply them. So for sine z dz, for y squared dy, and for x dx. Then we will multiply each of the results so that our final result will be 2/3. So as a summary, we're able to review differential calculus and integral calculus. Take note that this is already a review. That is why you have to look also on your previous notes in order to understand the topic in detail.